So we're told the mass of the beverage, and we're told the mass of the arm itself. So the mass of the beverage M1 is 5 kilograms, or where am I doing here? 2 kilograms. And the mass of the arm/hand amalgam is 1.2 kilograms. So we're looking for 3 things here. We want to know the force in the muscle, which we're modeling as a rope, which is appropriate because muscles can only pull on things. Muscles can't push on things. So I'm going to call that tension CD. And we want as, in component form, what the forces on the elbow joint are. So BX and BY, since we're going to model it as a pin joint. Right, so using the structural analog, we want to draw the free body diagram of our system. So before we draw anything, we want to select what's going to be the object of interest that we're isolating from all of its connections in this problem. Well, it's a rigid body, so it's not a point that we're going to be isolating. Oh, beam. Yes, yes. Right, the beam, well, so do we want the beam or the beam and the cord? Both would be okay. Both we could draw a free body diagram of. Yeah.
Can we just get rid of the cord because we might that instead of the cord?
Right, so if we take only the beam, get rid of the muscle, then we'll have the force that the muscle exerts on the beam. Or I'm combining the structural and the biological. So in the structural one, just the beam, take away the force, and then we'll have the force in the rope, which is the tension in the rope, TCD. So right, just the beam is what we want to use as our object of interest here. If we kept the rope, then we'd have to disconnect the rope from D, which is a pin, which is going to have 2 unknowns there, which we're not even asked for what's happening at the pin at D, which would be where is the muscle insert at the shoulder. But that will be a different question. So right, for the free body diagram, we're going to use the beam. So take a couple minutes and draw the free body diagram based on the beam being our object of interest here. Right, so the force from the muscle or the rope in the structure. So we don't know its magnitude, but we do know its direction is 75 degrees. Right, so to 3 digits, 11.8. Right, so again, we only want the weights of these objects. So this is the weight of the arm itself and the hand that we're going to model because we're going to see it's not radically different, or it's not radically smaller than the object that we're holding. So what other force do we need? Right, so the force of the Mountain Dew Extreme. So it has a mass of 2 kilograms, so it's going to have a weight force of 19.6 newtons. All right, so again, it's not even twice the mass of this. When we're talking about actual structural members in like a bridge, the weights of the members themselves might be like 1% of the force that they're holding up of cars or things like that. So in those cases, if it's like 1%, we usually neglect it for simplicity in our analysis. Here, it's about 50%, so we don't want to neglect it. Right, so B, so we're not done yet. Right, so B, we disconnected from the pin. So what do we have to have it be to model that pin that used to be connected to? Right, so the pin is restricting force in all directions in the plane. So for the pin, usually the easiest way to do it is we'll model it as its components, and then if we want to know the magnitude, we'll get that out at the end. Right, so this is our complete free body diagram. We have our dimensions, so the lengths of segments of our beam. We have this 75 degrees, coordinate system, everything's labeled, and our numbers are down, and we have our original object. Right, with our complete free body diagram, now we can write our equilibrium equations. So out of habit, I write Fx, Fy, moments about a point, but the order you do it in does not matter. In fact, it's sometimes easier numerically to start with the moments about a point, because we'll see in this problem that that's where we're going to get our first number out. But again, we can kind of write them, put them away, and then come back to them, whichever you prefer to work. So in the x direction, looking at our free body diagram, we'll have all of Bx and we'll have sum of TCD, so TCD cosine 75. Oh, and going back a moment to the free body diagram, again, making the assumption Bx is right, By is up. It could turn out at the end that I'm wrong, but out of, again, habit or consistency, I, for a pin, assume that they're along the positive directions because I don't necessarily know until the end what direction they're actually around. TCD, however, I know has to be pulling because it's a rope or a muscle, which can only pull, it cannot push. All right, so equation 1, I have two unknowns, one equation, so I can't get anything out of it at the moment. So I'll just leave it as it is. In the y direction, I have the weight of the beverage down. I have the 11.8, the weight of the arm down. I have the vertical component of the muscle up. And the way I've modeled By or assumed By, that's also up. So between my two equations, I have three unknowns. So I'll hold off and see if I get kind of a break on equation number 3 to crack this open. Questions about the first two equations? All right, so this is where we have a little bit more freedom. We can take the moment about any point that we want, and it's going to be equal to 0 because we're in equilibrium. So based on the free body diagram, what point algebraically is going to be the best point to take the moment about? Right, B, again, in 2 dimensions, if there's a pin, probably that's where you're going to want to take the moment about. But again, I'll reiterate, we could take the moment about C or G2 or A or any point in the world, and this will still be a true expression, just not as convenient for us to solve by hand. So picking a pin makes it convenient to solve by hand. So what's the right-hand side of this equation going to give us? Right, so a force, so that's the vertical force. It's a distance of 65. I will explicitly here put millimeters because I did not convert into meters. It can get confusing if your length measurements are in one base, like millimeters, and then if we had a couple in Newton meters, we want to make sure that everything's compatible. So I do want to keep track that this is in millimeters here. And then, correct, this is going to be a negative moment, because if we look at the vertical component, around point B, it wants to go clockwise, and counterclockwise is our assumed direction of positive. All right, so a force, it's times its distance, and it's clockwise. What else is on my right-hand side in this?
Plus 11.76.
Right, so the force due to the weight of the arm, a distance of 200 from B, and this is positive because it creates a counterclockwise moment around B. And then one more thing on the right-hand side. Right, so again, the weight of the beverage. As a check, these are all in millimeters, so everything at least lengthwise is compatible here. So as long as everything's in millimeters or everything's in meters, we're okay to use this. So because we've selected point B to take the moment about, equation number 3 is convenient because it has only that one unknown, TCD. So solving equation 3, we'll get that the tension in the muscle, in the bicep, is 131 newtons. If we put that into equation 2, we get that By, the vertical component of that pin, is negative 95. And if we put that into equation 1, TCD into equation 1, we'll get that Bx, negative 34 newtons.